Hello students, let's go to the next chapter of our syllabus. Today we are going to start a new chapter that is nothing but what? Thermal properties of matter. So here in this chapter, thermal properties of matter means what? How the properties of matter get changes with change in temperature, that we have to learn under this chapter. There are different aspects of these chapters are there, but here due to this COVID-19 pandemic, some point gets skipped in this. If you see in your book, directly the chapter will started, they have just skipped all the point. They just started from page number 121. There's one first topic, that is thermal expansion. So this chapter actually start here at this point, thermal expansion. Before this, what are the concept they have mentioned in your book, that are the basic concept related to change in temperature. So if you have time and if you have time permit you to do it, just read once. Whatever topic they have just taught before to this, just you have to read it once. One of the most important topic in that is what? Conversion of temperature from degree Celsius to degree Kelvin, and again it is into the degree Fahrenheit. There is one equation in your book, equation 7.3. All of you have to remember that equation. The page number 120, equation 7.3, that is TC for temperature in degree Celsius, TF for temperature in degree Fahrenheit, and TK for temperature in degree Kelvin. And this single equation gives you the relation between, you can find out the relation between temperature in degree Celsius to Fahrenheit, Fahrenheit to Kelvin, Kelvin to degree Celsius. So you have to remember this equation. So it will be better to remember this. Now let's start with the actual chapter, thermal expansion. Now the first topic of this chapter, according to this the syllabus, this is nothing but what? Thermal expansion. As all of you are well known about this, thermal means what? It is due to temperature. Expansion means what? Extension or elongation produced in a material due to temperature. That is said to be thermal expansion. One of the best example we'll see for this. Suppose we blow the balloon. When we blow the balloon, suppose the blowing the balloon, it become like this little bit. Suppose we have blown the balloon and it become like this. So this is the balloon we have blown. Okay. When this balloon was kept in refrigerator, when the same balloon was kept in refrigerator, especially in the region of refrigerator where we create a ice. Okay, freezing compartment, we have kept this balloon. We can see that this balloon becomes very small now. When we keep this balloon in refrigerator, especially in a freezing compartment, the bigger balloon becomes a smaller one. What does it mean? It means what? Due to this is the balloon at room temperature we have blown. Room temperature we have blown. When we kept it at the refrigerator, the freezing point, we can say approximately -4 to -6 degrees Celsius, it is seen that the size or volume of balloon get decreased. What does it mean? It means what? Due to change in temperature, here the volume of balloon get decreased. Again, after some time, you remove this balloon from the refrigerator and put it in the atmosphere. It is seen that within 10 to 15 minutes, it again regain its original shape and size, like this. Volume get increases. So this is said to be contraction. This is said to be contraction. Bigger to smaller, it become contract. Smaller to bigger, it's said to be expansion. Bigger to smaller, contraction. Smaller to bigger, it is expansion. So point to be remember, when the bigger object is converted into smaller, what should be there? Temperature decreases. Smaller object goes to be bigger one. What would be there? Temperature increases. And this contraction and expansion of material according to temperature is said to be expansions or contraction of the material, and that we have to learn under this chapter. So before going into detail of this, so here in this thermal expansion, so materials may be the solid, may be the liquids, maybe the gases, they get expand as well as they get contract according to change in temperature. Basically they have mentioned in this, after this topic, just told you that there are specifically 3 expansion they have studied. What are the 3 expansion? Linear expansion, the areal expansion, and the volume expansion. Definitely linear expansion means what? Change in length. Areal expansion means what? Change in area. Volume expansion means what? Change in volume of material. So let's start with the first one, change in length of material, that is said to be linear expansion. So suppose we have the rod like this is the rod we have, and this rod has an initial length. Suppose this length of the rod is, suppose small l is the length of the rod. When you change the temperature around this rod by an amount delta T is a change in the temperature, it is seen that we have increased the temperature. It is seen that rod get elongated and there is change in the length of delta L is a change in the length of the rod. When you increase the temperature, the elongation in the rod get occurred, and due to this elongation, the elongation means what? This will occur due to change in temperature. We have increased the temperature, length of the rod gets increased by an amount delta L. So this is said, delta L is said to be change in length of an object. Then here, one thing we can write, we have to derive the equation for linear expansion. So from this we can say as change in length delta L per unit original length L, delta L by L, change in length per unit original length. This change in length occur due to this temperature. So this must be directly proportional to temperature. If we increase the more temperature, more elongation will be there. So in that fashion, you can say change in length per unit original length directly proportional to change in temperature. Suppose I have removed this proportionality sign, I want to use some equality sign, I should consider one constant, and that we can write here like this, delta L divided by L is equal to some constant of proportionality, it is alpha. This is proportionality sign. This is a constant alpha into delta T. This alpha is said to be coefficient of linear expansion. Alpha is said to be constant of proportionality, or sometimes it is said to be coefficient of linear expansion. It depends, value depends on the material. Which material is used to make this rod, that will decide the value of alpha. Now here, under this topic, we can write from this equation, you can just find out the value of alpha. You can find out the value of alpha. So alpha equal to delta L divided by L into delta T. Just delta T goes to denominator. You can write alpha equal to delta L divided by L as it is, divided by delta T comes here. That will use the value of alpha. Same thing can be written as delta L means what? Change in length. Change in length. Initially the length is this much. After this temperature, length get increased. So there is a change in length. If we represent this change in length in terms of like this, L suffix T minus L suffix 0. L suffix T minus L suffix 0. What does it mean? Length of a rod at a temperature T, length of the same rod at a temperature 0 degrees Celsius. So this higher temperature length minus lower temperature length, that will give what? Increase in length or change in length, that is said to be delta L. And here this L means what? Original length at 0 degree, so it should be L0. Divide by L means divide by L0. Delta T is what? Change in temperature. Suppose higher temperature is T, minus lower means 0 degree Celsius temperature is T0. So the point to be remember in this equation, LT is the length at a temperature T. L0 is the length at a temperature T0, that is a 0 degree Celsius. So this is L0 means length at 0 degree Celsius. So change in length is LT minus L0 divide by L0 into T minus T0. We can write this equation. What is the meaning of this? They have just told you same thing in your book also. And after that, if in this equation, if we put here original length, if original length L0 is 1, original length L0 is equal to 1, and change in temperature, this that is nothing but what? T minus T0 is equal to 1 degree Celsius. Suppose original length is 1 meter or centimeter, whatever it may be. T minus T, change in temperature 1 degree Celsius. Then you can write this as alpha equal to what? You can write the equation alpha equal to this LT minus L0 is remaining. So it is LT minus L0, LT minus L0 Just I will write once again. This can be written as LT minus L0 divide by L0 we assume 1, T minus T0 we assume 1. So this is said to be approximate value of coefficient of linear expansion alpha equal to LT minus L0. And just below this, numerically we have written this. Below this just they have given a definition in bold black letter. What is the definition? I will read it. Coefficient of linear expansion of solid. Coefficient of linear expansion of solid is thus defined as increase in length per unit original length at 0 degrees Celsius per degree rise in temperature. Per degree rise in temperature. That means what? Coefficient of linear expansion is thus defined as increase in length per unit original length at 0 degrees Celsius for 1 degree rise of temperature. Just this is the definition. Increase in length per unit original length at 0 degrees Celsius per degree rise of 1 degree Celsius temperature of the body is said to be coefficient of linear expansion. Now if we see here, we assume this LT is a length at temperature T, L0 is a length at temperature 0 degrees Celsius, T0 that means. But we know that practically 0 degree is not possible. At a room temperature, it would be at a room temperature. Maybe it would be at room temperature. So same equation you can modify. Just you can write the temperature other than the 0 degree Celsius you can take. Then the same equation can be written as L2 minus L1 divide by L1. L2 minus L1 divide by L1 into T2 minus T1. Now these temperatures are other than the 0 degree Celsius. Now what are these temperatures? L2 is a length at temperature T2. L1 is a length at temperature T1. L2 is a length at temperature T2, higher temperature. L1 is a length at lower temperature T1 other than the 0 degree Celsius. So this is said to be thermal expansion, and especially we have learned linear expansion. This is related to linear expansions of material. Now remember, linear expansion it is said to be because it is related to change in the length of a material. That's why it is said to be linear expansion. By the same method, we can represent the same method to derive the same configuration for little bit change in area. Whenever there is a change in area, another concept comes that is said to be areal expansion. Before going into detail of areal expansion, in this linear expansion there is one table 7.1 in your book. In that table they have given different material and the value of their linear coefficient of expansion they have given. Okay, now again apart from this, if we see here, one thing is remaining. That what is the thing is remaining? We want to tell you what is the unit of this. If you see this change in length divided by length, if this is in meter, this is in meter, meter get cancelled out. What is remaining? 1 divided by temperature is remaining. So the unit of alpha is per degree Celsius or per degree Kelvin. Per degree Celsius or per degree Kelvin is a unit of this coefficient of linear expansion. Now the second part we have to see, that is nothing but what? Areal expansion we have to learn. So let's start with the areal expansion. Within this small part we'll start. So let's start with here areal expansion. So as its name suggests that it is areal expansion means what? There must be change in the area of the material, and that can occur due to change in temperature. Sometimes it is said to be superficial expansion. Superficial expansion also said to be as a areal expansion. So suppose we have one small metal plate. I will write it here. I will draw it here. This is a metal plate, small metal plate we have. Due to some change in temperature, if the area of the metal plate get increased, this is the increase in area of the metal plate due to change in temperature. The smaller one is the initial plate, the larger one is a change in area of the same metal plate due to increase in temperature. Delta T is an increase in temperature, and here change in area, suppose this initial area is A and this change in area is delta A, then change in area delta A and divide by original area A must be directly proportional to temperature. In case of length, we have taken delta L by L directly proportional to delta T. Here delta A by A directly proportional to delta T. Again, I want to remove this proportionality sign. You can write this as delta A divided by A must be equal to some constant, that is this is said to be beta, constant of proportionality, or the constant is set to beta into delta T as it is. Again, initial to same to initial one, just find the value of beta. So we can write beta equal to what? Delta A divided by A into delta T. Same thing we have written for a length, same thing we have written for a change in area. Now here delta A means what? Change in area, final area minus initial area. So what is this? AT minus A0, AT minus A0, change in area, divide by original area, means it is A0, and here temperature is what? T minus T0. This is again the same value we have written for a length. Now let's point to remember. AT is the area of the metal plate at a temperature T. A0 is the area at temperature T0, which is 0 degrees Celsius, we assume here. So we can write this equation for a beta. Again, this area, change in area divided by area, their unit get cancelled out. Unit of beta is again per degree Celsius. 1 divided by degree Celsius, that is per degree Celsius or per degree Kelvin. Now here, again we can write the same thing. If suppose here A0 is 1, T minus T0 is 1 degree Celsius. When this is 1 meter square, area would be 1 meter square, then we can write this beta as equal to change in area AT minus A0. That is numerically we can write this if A0 is 1, T minus T0 is 1. Now here, as we started here that T0 and A0 are the temperature and area at 0 degree Celsius. But at room temperature, area may get changed. It may be other than the 0. So the same equation we can write here. I will write beta equal to A2 minus A1 divided by A1 T2 minus T1. If you see this, you can say A2 is the area at temperature T2, A1 is the area at temperature T1, other than the 0 degree Celsius we can say. So this is nothing but what? The coefficient, this beta is said to be constant of proportionality or said to be coefficient of areal expansion or superficial expansion. Just see, they have given a definition. I will read it from your book. Coefficient of areal expansion of a solid is defined as increase in area per unit original area, increase in area per unit original area at 0 degrees Celsius for 1 degree rise in temperature. This is the formula they have used. Increase in area per unit original area at 0 degrees Celsius per degree rise in temperature. That is said to be coefficient of areal expansion. I hope that you got this linear expansion, you got this areal expansion. Once you got this two type of expansion, third one is very easy to understand. I think it is not essential to told you. You can do it at your home also. Still we revise it. Third type of expansion, that is said to be volume expansion. So just I will write here, it is third type. It is said to be volume expansion. So it is volume expansion, and that is the third type of expansions of a material. If there is change in volume, it is said to be volume expansion, and sometimes it is said to be cubical expansion. Cubical expansion. So this is the volume expansion or cubical expansion where there is change in the volume. Areal expansion, change in area. The linear expansion, change in length. So same to this. If we have a cube like this, I will draw the cube here. Suppose I have drawn the cube like this. So this is the first term we have drawn. The second part I have drawn here, and just connect them like this. We get here this as a cube. This is the cube. Suppose initially the cube is shown like this. So this is the cube. Then I have just written this as like this. Suppose this is a cube. We have this as a cube. Now when This volume of the cube is suppose V. If we increase the temperature, this cube volume get increased by amount dV due to change in temperature dt. Then again similar to initial one, we can write this as change in volume divided by original volume, means delta V divided by V. This must be delta V. Change in volume divided by original volume is directly proportional to temperature. So again, this temperature, I want to remove this proportionality sign. You can write delta V divided by V is equal to, this is the constant of proportionality, into delta T should be the time. So this should be delta T. So gamma is said to be constant of proportionality, or it is said to be constant of volume expansion or cubical expansion. Now again, just we have done initially, same, find out the value of gamma. So gamma equal to what? Delta V, change in volume, divided by original volume, divided by delta T. This move to this side, it become like this. Now we can put its value at 0 degrees Celsius, just we have done in linear and areal expansion. You can write this delta V as Vt minus V0 divide by V0 T minus T0. Now see, Vt is volume at temperature T degrees Celsius. V0 is volume at temperature T0 degrees Celsius. So this is the formula we have written for a gamma. Vt minus V0 divided by V0 into T minus T0. Now this coefficient of volume expansion can be explained as increase in volume per unit original volume at 0 degrees Celsius per degree 1 degree rise in temperature. That is said to be coefficient of volume expansion. Increase in volume per unit original volume at 0 degrees Celsius for 1 degree rise in temperature, that is said to be coefficient of volume expansion represented by gamma. Again, if you put V0 equal to 1, T minus T0 equal to 1, you can write gamma equal to what? Increase in volume, Vt minus V0. Numerically, you can write like this. Here we have taken V0 as a temperature and T0 as a temperature and V0 as a volume at 0 degrees Celsius. It may be other than 0. So you can modify this. I will write this gamma equal to V2 minus V1 divide by V1 T2 minus T1. So this is the modified formula for another temperatures and volume other than the 0 degrees Celsius. Vt is a volume at temperature T2. V1 is volume at temperature T1. So here V2 minus V1 divided by V1 into T2 minus T1. And this is said to be volume expansion. Volume expansion we can call it as, or this, in this fashion we have learned the thermal expansion we have started, and we have learned the three type of expansion: the linear expansion, the volume expansion, and the areal expansion, and we have derived the equation for each of them. Now if we consider this, it's very simple parameter. After every expansion they have given the values, they have given one table, and that table they have given a material, and they just try to find out the value of alpha, beta and gamma they have given. Apart from this, in case of alpha is the coefficient of linear expansion, beta coefficient of areal expansion, gamma coefficient of volume expansion, that we have learned. After that, in the same topic in your book, just they have given the relation between this. They have find out relation between coefficient of expansion. You have to remember only one equation, that is on page number 125, equation 7.25. No need how it is derived. You have to remember the equation directly. So what is the equation? Alpha equal to beta divided by 2 equal to gamma divided by 3. Alpha equal to beta by 2 equal to gamma by 3. Alpha is a linear coefficient of expansion, beta is a areal coefficient of expansion, gamma is a volume coefficient of expansion. So this formula gives the relation between all these three parameters. Suppose I want to find relation between alpha and beta only. What we can write? Alpha equal to beta divided by 2. This implies that beta equal to twice alpha. If I want to find relation between these two, beta and gamma, what we can write? We can write here beta by 2 equal to gamma by 3. Okay, we can write this as beta equal to 2 by 3 gamma, or you can write gamma equal to 3 by 2 beta. In this fashion, this relation can be found out once you remember only one equation, alpha equal to beta by 2 equal to gamma by 3. This is very easy to understand. How can you understand? Alpha divided by 1 equal to beta divided by 2 equal to gamma divided by 3. 1, 2, 3, alpha, beta, gamma. That's it. Anything number divided by 1 means we can represent it as simply alpha. In this fashion, you can remember this relation between these three coefficient of expansion, linear, areal, and the volume expansion. You have to remember that. Now, if you remember, just turn the pages from your book. When we have seen coefficient of linear expansion, below that there is one numerical on the equation of alpha. After coefficient of areal expansion, there is solved numerical on the value of beta. Coefficient of volume expansion, there is solved numerical on the value of gamma. It is very easy to understand that numerical. Go to that numericals, try to understand what they have done, how they have put the values, how they have find out the resultant answer. Once you do it, it is very easy to understand or solve the next numericals in your book. Whatever the numericals are there in exercise, you can able to find it out. Let's go to next topic, specific heat capacity. Let's go to next topic, specific heat capacity. What exactly specific heat capacity is, that we have to learn under this. So specific heat capacity, before going into detail of this, in your book they have given one of the best example, and we start with that example. Suppose we have 1 kg of water, we have taken 1 kg of water we have taken, and 1 kg of paraffin we have taken. In your book they have taken example of paraffin. So 1 kg of paraffin. These are the materials we have taken. One is nothing but water, other is nothing but that paraffin. Just a specific heat capacity. Under this, first we have to see specific heat capacities of solids and liquid. Then we go for gases. Specific heat capacity of solids and liquids. In that, just they have taken an example. If we have 1 kg of water and we have 1 kg of paraffin. Okay, 1 kg of water, 1 kg of paraffin, and we have the heater. We are going to heat this water and paraffin at the same time. We are going to heat this 1 kg of water and 1 kg of paraffin for same amount of time, and same amount of heat is supplied. Suppose I have supplied, this is nothing but a heat supplied to this, and for time t I have supplied this heat. Same amount of heat is supplied to paraffin, and same amount of time we have supplied the heat to paraffin. Both materials are same in amount, 1 kg water, 1 kg paraffin. We have supplied heat to water and paraffin, same amount of heat is supplied by heater, and for same amount of time, same time we have supplied same heat to the different material. Then probability is what? Whatever the change in temperature of water, that must be same as temperature in paraffin. But practically it is seen that if temperature of water increases by 1 degree Celsius for this time, for this heat, it is seen that for paraffin, for same time and same heat, the temperature increases by double of the water. Suppose in the case of water, due to this time, due to this heat, and for this time we have supplied, the temperature of water changes by due to after this time the temperature becomes suppose 10 degrees Celsius in case of water. For same heat and same time period, if we give to paraffin, it is seen that its temperature changes to 20 degrees Celsius. Double of this temperature of paraffin changes double of the water. Now the question comes, why it's so? We are supplying same heat for same time period here and here. Still the temperature of water increases by 10 degrees Celsius, but temperature of paraffin increases double of the water, that is 20 degrees Celsius. Reason behind this what? Every material, maybe solid, liquid, every material has one constant, that one value that is said to be specific heat capacity. Specific heat capacity of water is different. Specific heat capacity of paraffin is different, and that's why the temperature of water increases by 10 degrees Celsius due to this heat in time t. while paraffin, it increases double of water because of this constant specific heat capacity of water, and these paraffins are different. And that's why it's very essential to learn what is specific heat capacity. So this is one of the example why it is essential to learn this specific heat capacity. Now let's start with in detail specific heat capacity of solids and liquids we have to learn. Now in this specific heat capacity, if delta Q is amount of heat supplied or extracted from a material, supplied or given out, taken out from a material, delta Q amount of heat supplied or taken out from a material of a mass, the material has a mass m, delta Q amount of heat is supplied for a m mass of material, or delta Q amount of heat is taken out for m amount of mass of material, and they do, while doing this there is change in temperature delta T, then amount of heat supplied or given out divide by mass into change in temperature. This ratio is always said to be the specific heat capacity represented by S. Specific heat capacity is ratio of amount of heat absorbed by the material or taken out from the material per unit mass of the material per unit change in the temperature of that material is said to be specific heat capacity of that material. Another way, below this in your book, just how to modify this little bit. If here this mass is 1 kg of mass we have taken, and the change in temperature could be 1 degree Celsius. 1 degree Celsius change in temperature is there for 1 kg of mass, then we can write specific heat capacity is equal to delta Q, amount of heat supplied or amount of heat given out, taken out from a material. Now below this they have given the definition. I know that you didn't understand anything in this. I will tell you now. Amount of heat supplied to the material, amount of heat supplied to material of 1 kg mass to increase its temperature or decrease its temperature by 1 degree Celsius, amount of heat supplied is said to be specific heat capacity of that material. In short, any material we have taken, how much amount of heat should be supplied to that material to increase the temperature of that material by 1 degree Celsius or decrease the temperature of material by 1 degree Celsius. I will try to explain it. Suppose this is a material we have. This is a material we have. Suppose this is a material or this is substance we have. Amount of heat supplied to this material means this. Suppose initially before applying this temperature here, the temperature of substance is suppose 20 degrees Celsius, or suppose it is 30 degrees Celsius. This is the temperature of substance. Now what we have done, we start heating this material. Supply the heat delta Q. But the condition is what? When you supply the heat to substance, supply the heat delta Q so that the amount of substance, the temperature of substance change from 30 to 31 degrees Celsius. 30 to 31 degrees Celsius. How much temperature change? 1 degree Celsius rises. So this amount of heat delta Q supplied to this material for which temperature changes by 1 degree Celsius, then this amount of heat supplied is said to be specific heat of this substance. Specific heat of this substance. This is the case to increase the temperature. Is it? Another thing, suppose we have this another substance. This is another substance. Its temperature is again 30 degrees Celsius. Okay, we are not going to supply the heat. We are going to extract the heat. Extract means we are removing the heat from a material so that temperature changes from 30 to 29 degrees Celsius. Here there is what? Fall of temperature. We have decreased the temperature of this substance by 1 degree Celsius by taking some heat from this. Just we are removing some heat from this, that is said to be heat taken out from a material to decrease the temperature by 1 degree Celsius. The amount of heat taken out is delta Q, and this is said to be specific heat capacity of this substance to decrease the temperature by 1 degree Celsius. To increase the temperature by 1 degree Celsius, this much amount of heat is supplied. So this is specific heat capacity to increase the temperature. to decrease the temperature, this much amount of heat is taken out from a substance, then this specific heat capacity to decrease the temperature of body by 1 degree Celsius. While doing both the cases, this substance is how much amount? It is 1 kg. This again 1 kg. Okay, so this is nothing but specific heat. I think you got a better idea, better understanding by this example. I hope you understand what is meant by specific heat. Specific heat capacity means amount of heat supplied to the material or taken out from a material to change the temperature of material by 1 degree Celsius. Then that amount of heat given or taken out is said to be specific heat capacity of that substance, of that material. So I will read from the book. Thus the specific heat capacity is defined as amount of heat per unit mass, amount of heat per unit mass, delta Q by M. So amount of heat per unit mass, this is nothing but that. So specific capacity is defined as amount of heat per unit mass absorbed or given out, absorbed to increase the temperature, given out to decrease the temperature. So defined as amount of heat per unit mass absorbed or given out by the substance to change the temperature by 1 unit, 1 degree or 1 Kelvin. That amount of heat supplied or absorbed by the material or given out from a material is said to be specific heat capacity of that material. Below that, there is one table 7.6. In this table, they have given a substance. They have given different substance, different material, and they have just mentioned there the value of specific heat capacity of that materials. Now it is seen that for steel it is 120, and at the last it is water. For a water, specific heat capacity is 4186. So for a water, specific heat capacity is very large, and this is the reason why the water is used as a coolant in automobiles. In the automobiles, we are using the water as a coolant. Why? Because their automobile engines are heating. So there is one radiator part of the automobile cars, vehicles, radiator. So to make the engine cool, basically they will use this water, because specific heat capacity of water is very large. So water behave as a coolant. It will cool the engine. So it is used as a coolant in radiator in automobiles. Now what should be the unit of the specific heat capacity from this formula? Amount of heat supplied, this delta Q is amount of heat supplied or taken out. It is measured in joule. This mass is in kilogram, and this temperature is in degrees Celsius. So unit would be, this can be written as joule per kg per Kelvin or degrees Celsius. Degrees Celsius, or you can write it Kelvin also. So you can write here unit of specific heat is joule per kg per Kelvin per kg per degree Celsius, or it is said to be joule per kg per degree Kelvin. This is the unit of this specific heat capacity, SI unit, or it is said to be SI unit, or it is said to be MKS unit. What is the unit in CGS system? The joule, there must be what? Erg. For this joule, there must be R per gram per degree Celsius, or erg per gram per degree Kelvin, per degree Kelvin. That is a CGS system, CGS system, CGS system. Okay, it is in Kelvin, it is in degree Celsius. That's it. So these are the MKS system unit. These are the CGS system unit for this specific heat capacity. Now here, if you remember, we are going to use here this mass. This mass we have taken in kilogram. This mass we have taken in kilogram. Instead of kilogram, suppose I am going to take a mass in mole, molar. This might be you have learned in chemistry. You can take mass in molar. If instead of this kilogram, we have measured the mass of material in mole, then that mole was represented by mu mole. Instead of m mass in kilogram, we are represented by mu amount of mole. Then you can write this specific heat capacity as you can write as S, or just basically they have used both symbols here. as they have used here, basically it should be C. Specific heat capacity it is na, it should be C. So you can write C equal to specific heat capacity equal to 1 by M. You should write 1 by mu. So 1 by mu delta Q as it is, delta Q divided by delta T, or we can write here like this, delta Q divided by mu into delta T. Mu is what? Mass of a material in mole. This is in mole. Okay, mole we can, molar mass we have taken instead of kilogram. Then that type of specific heat is said to be, there are two type of specific heat. There is one said to be molar specific heat. If you measure the mass in mole, it is said to be molar specific heat. Why it is molar specific heat? Because we are going to measure the mass in mole, molar specific heat. And when you are going to measure the mass in kilogram, it is said to be the principal specific heat. Principal. So this is principal specific heat. This is a molar specific heat. Is it? Now you get the idea why the symbols are different. S is a symbol for principal specific heat. C is a symbol for molar specific heat. What is the difference? Difference is only here it is 1 kg, mass is measured in kilogram. Here the mass is measured in molar. That is nothing but a molar specific heat. That is molar specific heat, and kilogram principal specific heat. So point to be remember, there are two type of specific heat. The principal specific heat in which the mass is measured in kilogram. Molar specific heat in which mass is measured in number of moles, and definition remains same. So only modification is there. What the modification would be per unit kg of mass, instead of that kg, per mole of mass in another definition per mole. That we'll see in further we have the different types they have mentioned for specific heat. In detail we'll see in that topic. So I think the video becomes very longer today, so it is better to stop here. In next period we'll see what are the different type of specific heat. These are we have learned up till now the two type of specific heat. Principal specific heat, mass is measured in kilogram. The another is molar specific heat, mass is measured in mole. So these two specific heat for solids and liquid we have learned. Next topic we will see specific heat capacity for gases, and how they are different definitions they have given, that we have to see further. So I think it's better to stop here. Now just you watch my video. Once after watching the video, try to read the same topic from your book for your better understanding. Still, if you have the query, you feel free to ask me anytime. Thank you.